Hello, everyone. Today I will be talking about the International Year of Quantum 2025 because it's pretty cool. So let's get to it. As a preface and to prime you for the rest of the video, I want to give a brief overview of the history of quantum mechanics. I believe this is important because the celebration I'll be talking about, the International Year of Quantum 2025, was chosen because this year was the 100th anniversary of quantum mechanics. And of course, quantum mechanics is a very broad subject. Its foundations in wave mechanics, specifically the double slit experiment we now know, love, and are probably getting tired of hearing about, were laid back in 1801. However, that doesn't really get much attention. Indeed, a lot of quantum history, which is covered in popular media nowadays, is actually relatively late developments, paradigm and interpretation arguments for an already pretty healthy theory. And while I am by no means the popular media, I would still like to talk about this nonetheless. And most of the information here will be sourced from Wikipedia's timeline of quantum mechanics, which will be linked in the description. So, the story of quantum mechanics really has three intertwining parts: chemistry research and the model of the atom, what we think of as mainline quantum, which originated from studies on black body radiation, and the development of Einstein's general relativity. In the early days, of course. Why Einstein's relativity is mentioned here? Well, not only did the man himself make significant contributions in the mainline research, in fact, also having been the first to propose, like, basically the photon or the idea that light could be quantized, but also, like, quantum gravity. Not to get too ideological, but I'm a believer that looking into the past can bring us closer to answers in the present, and that is why understanding this history is so important to me. A little known fact is actually that Einstein was working on a sort of unified theory in some of his final research. But yeah, the reason I bring up general relativity is because its development and impact on, well, physics as a whole is still being felt in current research on quantum gravity. But this is mostly all you'll hear about relativity in this video, so don't get your hopes up too high. All right. So, before the 20th century, the understanding of the structure of the atom really hinged upon the Rydberg formula. Aside from it, why chemical properties differed between different elements wasn't really known. What this predicted, however, are the wavelengths, or equivalently energies, of the photons emitted after an ionized atom of hydrogen falls back to its ground state, and these wavelengths are drawn as spectral lines, if you are familiar with what that is from maybe your chemistry class. Before Bohr's work on the model of the atom, this was just an experimental formula, and we didn't really know why it worked. But it did, and it gave us some idea into the energies of electrons within the atom. Yeah, so these spectral lines ended up being a pretty common thread throughout the development of not only the model for the atom, which we know now, right, involving orbitals, but also to the larger history of quantum mechanics. Um, and in parallel to this, Planck devised his quantization hypothesis in 1900 for electromagnetic energy to describe black body radiation, or why things glow when they're heated up. As I mentioned earlier, Einstein would actually use this hypothesis to predict the photon 5 years later. Oh, and he published Special Relativity the same year. So just a fun fact for you. But okay, in all seriousness, this was monumental. Like, I cannot understate that, or overstate that. Overstate. I think overstate. Okay. I know how to speak this language, I promise. Um, so yeah, in the early days, this is what quantum research was about. Now, arms race to chuck Planck's quantum hypothesis at as many things as possible to basically make photons and electrons less lonely and to have a more complete theory surrounding them. Around this time, another pillar was formed, that being wave-particle duality, discovered by Jeffrey Ingram Taylor in 1909. He did this by basically performing a version of the double slit experiment using just one photon, or yeah, performing the double slit experiment we know now. Um, fascinatingly, without actually seeming to know what a photon is, or at least not mentioning it or Einstein's postulation on it in his paper. So, yeah, great minds really do think alike. The foundations for the discovery of the neutron and the neutrino as well would be laid in 1911 by Lise Meitner and Otto Hahn, when experiments showed that the spin of atoms, because apparently spin was already discovered, that was a surprise to me when I was researching this, did not align with that predicted by the Rutherford theory at the time, which didn't account for neutrons. And neutrinos get lumped into the slide as well, because of beta decay shenanigans involving experimental testing of the quantization of electron energy, something like that. So to fix this, in 1913, Niels Bohr published his model of the atom, which is what we now know and love in all its orbitals and nucleus glory. Even though prior planetary models also had orbitals, what they were missing that Bohr had was a definite structure to where the electrons were, and that structure corresponding to the energy of the electrons. The last thing I want to mention for the 1910s is that Einstein published general relativity. Go fish. Later in the 1920s, most of what you may already be familiar with happened. So that's bosons, Bose-Einstein condensates, Pauli exclusion principle, the canonical birth of quantum mechanics, which will be talked about in more detail, fermions, Schrodinger's equation, and the uncertainty principle. Schrodinger's cat, however, is allocated to later paradigm and interpretation debates. Thanks to Heisenberg and Bohr, it really wouldn't be the same without them, as is quantum entanglement. The thing I've been thinking about while researching this is just how fascinating it would be if I could have learned quantum mechanics already having the basis of chemistry. Like, it'd be fascinating to not necessarily like replicate, but kind of understand where quantum mechanics was coming from and be able to apply that to learning. Though I guess it could be just as fascinating for me to learn chemistry through the lens of quantum mechanics. Funny how it goes. All right, let's now get to the main thing I wanted to get to for this video. The International Year of Quantum 2025, the website for which can be found at quantum2025.org. Firstly, I am exceedingly aware I'm a bit late to this, considering the year is almost over and might already be over by the time I publish this, but looking back, I just wanted to point out how important these celebrations were. Also, there will still be events held in 2026, one of which is the closing ceremonies, because the year's not over until IYQ says it's done. So, time is a construct, firstly. Let's just get that out of the way. And yes, even though I've been calling them celebrations, it's more a massive education, science communication, and awareness campaign and platform as well for communicators to put their events on this Quantum 2025 website for them to be easier to discover. Right? So, as for why 2025 was chosen, 100 years ago in July of 1925, Heisenberg, July. This says December. Maybe I'm not so late after all. Okay. I don't know. Something I read said it was July. It's probably December. Heisenberg published his Umdeutung, or reinterpretation paper, which laid out not only the mathematical but also conceptual foundations for what is now known as quantum mechanics. Essentially, he translated or reinterpreted some classical concepts such as energy and momentum into the quantized realm, and his framework just worked. In fact, it worked so well that this paper is to some extent considered the birth of quantum mechanics, as is evidenced by the fact that, well, IYQ was held this year. An interesting tidbit of this is that nobody really knew why his paper worked, because the mathematical arguments behind the points he made were so loose that it actually took a little bit of time after the initial publication to get all the rigorous details out. Yeah, okay. Um, So another thing of history, which I got from CERN's publication on a century in quantum, is actually that at the time, Heisenberg and Pauli, who you may know from the Pauli exclusion principle, had a pretty strong friendship and rivalry. In this letter shown here, which I also got from the CERN website, Heisenberg argued with Pauli's point on how the electrons within electron orbitals actually behave themselves, but also he sent the original manuscript for this Umdeutung paper to Pauli to basically get his opinion. And I think it's just really cool to see the humanity behind the research and the history of the research. And we have to thank CERN for archiving this letter as well. All right, so what I find especially cool about this project and what caught my eye is that the whole thing advocates for open science and equality in science because all of these issues are interconnected. And as a representative of the woman myself, they're important to me because they will affect me personally later. And I know that makes me biased, but I'm still going to talk about it. Uh, the way this advocacy proceeds is firstly by centering developing and less developed nations, such as those in Africa, to help in ensuring they do not get left behind when wider adoption of whatever quantum technologies are developed comes. IYQ also partners with many organizations that promote open access and wider adoption of open access, as well as making that possible through, say, funding like IEEE. Uh, IEEE will be discussed in the last video as well. I have many things, many positive things to say about them. They also do, in fact, highlight women in the Quantum 100 section of the website, which is probably the bare minimum, but woo, nonetheless. Because, like, the thing with physics and quantum stuff is often it's not necessarily like its applications, but I think it's viewed, even in my personal experience dealing with people asking me why I want to go into physics, a lot of the applications are quite far removed. But IYQ 2025 sets out to communicate these applications and help the public understand why quantum research and quantum computing are so important. It highlights the very real climate and medical advancements that these could bring about, right? As you can see in these little cards here, screenshotted from their website. Um, Not only are quantum computers extremely powerful in terms of simulating chemical interactions, which could aid in developing medical drugs and testing their effects, but quantum chemistry itself is very much an active field of research, as we have already seen in the history of quantum mechanics. These two things are very much intertwined. Also, as mentioned here, quantum photonics is currently helping in medical imaging to spot various illnesses earlier and diagnose them more accurately. Another thing in medical related quantum physics intersection that I wanted to mention somewhere, and this seems like a good time, is the first proton arc therapy treatments for cancer patients were delivered this year. You can read the original paper and the coverage I learned about this from in the description. As you can see here, this is from Physics World. Okay, that's the next thing. Um, Let me see. Yeah, this website also points out the positive potential climate impacts that quantum technologies could have. Again, due to quantum computer simulating powers, we could have better simulations and predictions for weather events and the overall state of the climate soon. Not only that, but in the field of quantum engineering, research is being conducted on how to make, say, solar panels more efficient because even in my own personal experience working on a project that involved totaling up energy spending and production, I was literally told disregard the solar panels, which is crazy. Like, of course, I don't want to be cynical, especially considering this kind of research to improve them is actively being conducted. But up to that point, I feel like I was like perhaps naive, thinking they could just be a miracle cure for all the world's energy problems. But hopefully, as the field of quantum engineering advances, and crucially, there's more eyes on it and more funding for it, these advancements will make that the case. I think that's the clean energy one. I probably should have circled that, but I was too busy learning or trying to not forget how to use this language. And like really that's just the tip of the iceberg. I've basically only read like 3 or 4 points from this panel, right? And even that's heavily simplified because there's only so much you can fit into this little text. And even then, I think the IYQ people did a good job at summarizing this. I really don't know what else I could have added, but I don't know, maybe that's just a personal failure. Um, Now I want to talk a little bit about science communication because it's super important to me, and I'm not gonna make a dedicated video on this because nobody would watch that. But if I sandwich it between things you actually want to see, then I can say whatever. So for me, the thing with science communication is that I feel like I sometimes come off as hating it and hating science communicators and preaching for everyone to be an expert in every field. But that's like not the case. That'd be completely impossible. And the only reason I am able to go deeper into these subjects is because I want to pursue them in the future. In the same way that I don't expect like myself and you don't see me talking about subjects like biology or engineering or mathematics, I guess, or medicine, I wouldn't expect any other layperson to go around reading every paper they see being talked about in the news. You may be asking, like, if you watch some of my earlier videos, why I'm allowing myself to link to a news reporting about proton arc therapy, uh, if I like hate science news outlets so much, but and that's just because I too need science to be communicated to me before I know about it. In fact, it was quite hard to select the things to report on this year because my narrow area of like not expertise, but perhaps interest and the task of distilling only the most impactful and the most impactful research to talk about to try not to leave anything important out, like that was hard. And that's why I went against the format I want to establish of reading papers and trying my best to explain them because I frankly don't know how to weed out the ones that would actually be important. And what I'm trying to get at is it's not science communication that I have a problem with. It's clickbait titles and the overall lack of media literacy when it comes to science news. I feel like from anecdotal evidence, science is often left out in favor of discussing politics and spotting biases, which is of course important nowadays, and that's where our sponsor comes in. I'm kidding, I don't get paid for this. In any case, it's hard to expect the average layperson to read the full article nowadays, much less the actual research paper behind it, which, again, as I said, I don't expect anyone to do that. And that's not always necessarily the layperson's fault. Science is one of those things that shouldn't be met with skepticism 99.999% of the time, but it's hard to toe that line when it feels like skepticism is necessary to get to the bottom of what is actually being communicated. And this was also something that you will see in the microboon paper that I am going to be talking about in the third video of this like physics wrapped kind of thing. And arguably, like physics is the least affected by this. Of course, there are applications, uh, like that we say. Of course, like there are applications, and yes, they are important. But when day comes to night, physics and new physics is quite abstracted from our daily lives, unlike something like medicine, which people can literally die if something if someone believes a fringe theory, and arguably that is already happening around the world. Like, I just can't stay in my little bubble of particle physics when people are dying due to a deficit in proper science communication and a lack of media literacy. And yet I cannot on my own feasibly cover everything that those news outlets I'm begging that shall remain unnamed also covered and read all the papers which they read, right? And having said that, I'm just talking about what I find interesting, and I understand what I find interesting. Like, that's in my own particle physics bubble and will not be perhaps what's most necessary, important, or impactful to report on. This comes back to the fact that I too need science communicated to me and need someone who knows more about this stuff than me, who's actually involved in academic spaces to highlight the papers that will actually change the world the most for me, right? Okay, that's enough yap. Thank you. Returning back to the topic at hand, I have linked the recordings for a few of the events which are available on YouTube in the description. As will be mentioned in the last video on open access, this commitment to keeping information not only archived but also public, as well as presumably, don't quote me on this, I'm not a lawyer, allowing the speakers to retain the rights of the recordings of the lectures they gave is, to me, like the backbone of what the future of academia should be. Right, because these videos were all uploaded to presumably the science communicators' own channels. And I would specifically like to congratulate the Asian science community for holding the first Asian Quantum Summit this year, this December. Um, I wish I could have like been there, honestly. For those who don't know, I also live in Southeast Asia, so seeing this really warmed my heart. But yeah, lots of events on a huge variety of topics were held this year at the like official start on January 13th. The whole celebration was kicked off with many events across the world, as you can see. Just a few of them from the website screenshotted here, but there were some prior to this, some after this, but like the official start, right, as you can see right here. Um, so these were primarily talks, discussions, but I also saw like hackathons, and essay competitions, workshops, and a Wikipedia editathon. Try saying that 5 times fast, which is like so cool, and I would love to participate in one someday. These weren't all in those first few days, but just like throughout the year that I have selected. Um, there were also events in a ton of different languages. I saw ones in Turkish, French, Japanese, Italian, the whole lot, English, obviously. And also, I think one of the most telling things about how committed the organizers were to the mission of this project is that the events do not stop in 2025, as I mentioned. And in fact, the closing ceremony, the page for which is screenshotted here, will actually be conducted in February of 2026 in Ghana. The Ghanaian officials basically agreed to be the representative country for International Year of Quantum 2025, and I think that's pretty neat. So, on that positive note, I would like to move on to the next topic in the next video, the 2025 and 2024 as well, since I have some leftover opinions to share, Nobel Prizes. So see you there. Thanks for watching, and please check out quantum2025.org. I'm not paid by them, by the way. I feel like I should have said that earlier. So yeah, thank you, and see you in the next one, please.